relaxed state, so when muscle is relaxed, we know that those binding sites on actin are covered, okay? And why are they covered? Because there's no calcium bound to troponin. So calcium needs to be bound on troponin to move tropomyosin away from those binding sites. And in the relaxed state, that is not the case. Now, in the contracted state, in the presence of calcium, and we talked about how calcium got into the cytoplasm, right? So now calcium's in the cytoplasm, and it's free to bind to troponin on its binding site, which influences the movement of tropomyosin, which is also bound to this troponin complex. And that tropomyosin gets dragged off of those binding sites, and now they are free and open and accessible for myosin to bind, okay? And so this is how the presence and absence of calcium regulates this process. If we have calcium, we can bind actin to myosin, and if we don't have calcium, we cannot. Okay, very, very important to distinguish those two states. I hope everyone watched this video by now to sort of summarize excitation, contraction, coupling, and get a better sense of what's going on. The final bit of speaking about excitation, contraction, coupling is getting into the details of how that calcium leaves the sarcoplasmic reticulum. So we said calcium is being stored in the SR, and in order for muscle to contract, it has to leave the SR and go into the cytoplasm. This is where actin and myosin and these sarcomeres are, okay? And so we have these two structures that are in the SR membrane. It's the sarcoplasmic pump, okay? Not pump, sorry, excuse me, a voltage-gated channel. And so in the membrane of the T-tubule, linking to the membrane of the SR is this voltage-gated or voltage-coupled receptor here. And so what really happens is that action potential, and I'm using action potential and end plate potential interchangeably. They're the exact same thing here in muscle. It's going to move through the T-tubule, it's going to get through that muscle very quickly, and it's going to stimulate, because it's changing the voltage, this voltage-gated receptor to open. And the voltage-gated receptor is made of two components. There's a DHP part, dihydropyridine, sorry, this part in purple, and this is what is sensing the voltage change. And when DHP picks up a voltage change, it sends that signal to the ryanodine part of this receptor, which is actually nothing but a calcium channel. So DHP picks up a voltage change, sends that signal to ryanodine. Ryanodine opens up this calcium channel, and calcium can now move from the SR, right? This is representing the SR here, which is blue in this area, out into the cytoplasm, which is into this space, or this space here, which is out into the rest of the cell. So not out of the cell completely, but into the cytoplasm of the cell, okay? And this is how calcium moves from its storage area in the SR out to flood the cytoplasm, and it can then interact with actin and bring about cross-bridge cycling. So really important to understand the coupling of these receptors and how the voltage travels through those T-tubules, gets to these receptors, and stimulates that release of calcium. So we have calcium-induced opening and closing. In the presence of calcium, right, calcium can actually bind to some more of these receptors and stimulate this sort of positive feedback event where calcium begets more calcium, begets more calcium. We open up more calcium channels, and that stimulates a further rush of calcium. No, so the terminal cisternae would be this part of the SR. Okay, so this is where this calcium is actually being stored, the blue part here. This entire thing, yeah. So we said this is a triad. This is a lateral sac or a terminal cisternae. This is also a lateral sac, and in the middle is a T-tubule. So together those things form a triad, right? Whereas this receptor is studded in the membrane. The DHP part of the receptor is in the membrane of the T-tubule, and the ryanodine part of the receptor is in the membrane of the SR. And they're coupled together so that the T-tubule can communicate with the SR, essentially. When that voltage change comes through, it needs to signal the opening up of that calcium channel so calcium can do its thing, right? It has to get into the cytoplasm and bring about cross-bridge cycling. Any other questions on this? Any other questions? Okay, now at the end of all of this, and we kind of alluded to this last time, at the end of all of this, calcium must leave troponin. It must leave the cytoplasm. Otherwise, muscle will contract indefinitely. In order for calcium to leave the cytosol or the cytoplasm, it must be pumped out. And so we have these calcium ATPase pumps that are also in the membrane of the SR. So they're pumping calcium back into its storage area, which is in that sarcoplasmic reticulum. Please understand, they must leave troponin so that it can go back to its relaxed state, which is tropomyosin covering up those binding sites again, okay? And so when muscle is relaxed, that calcium pump gets rid of all that calcium from the cytoplasm back into the SR, and that is how we facilitate the cessation or the ceasing of muscle contraction or of cross-bridge cycling, okay? This is an active pump, hence ATPase, okay? So it's gonna be using energy. Any questions on those two bits? Any questions on those two things? So the coupling of those two parts of that voltage-gated receptor, and then the calcium pump on the membrane here, which is moving that calcium out of the cell. Okay.